At this point, you should know that you can solve a quadratic equation by completing the square, or by using the quadratic formula, or by factoring. Okay? Well, here we're going to derive the quadratic formula by completing the square. We start with a quadratic equation which generally has a form ax squared plus bx plus c equals 0, where a is not equal to 0. If a was equal to 0, we just have a linear equation and we wouldn't need any technique for solving a quadratic equation. Okay, so since a isn't 0, we divide both sides by a. That gives us the advantage that the expression we need to complete the square on is what I've underlined here in yellow, just the x squared plus b over a times x. Now here we establish that, well, again, you know from completing the square, and you should understand fully why this works, but if you divide the coefficient of x by 2, then this thing will be the beginning of a square of b plus x plus b over 2a quantity squared. So that, well, we can square this and we get this, and that should be very obvious to you. In other words, when we square this, we do get a b over a in front of x, and we do get just plain an x squared. So we get this plus a little extra, plus b squared over 4a squared. Well, subtracting b squared over 4a squared from this gives us an expression for x plus b over a times x. That's this. So subtracting this from both sides, well, we get this minus this, which I've got here. And now we continue the line of thought we have here. This is just a little help that we put down here in a different color and indent. But the solution to this equation continues from here to here now. And we replace this by this as we've seen. So now we have this here, which matches this here, and this here. And then we have our plus c over a. So we have our x squared plus b over x here. We have our c over a here. We rearrange this. We add b squared over 4a squared to both sides, subtract c over a from both sides. We get this, and we put this right-hand side here expressed in terms of the common denominator 4a squared. All we have to do is multiply numerator and denominator here by 4a. Our denominator becomes 4a squared. Our numerator becomes 4ac. So right there is a negative 4ac plus b squared over the quantity 4a squared. So taking this and this, we get this expression, just completely equivalent to what we have here. And why would we do that? Well, we do that because we know that if we have the square of something equal to another expression, then that something is going to be plus or minus the square root of that other expression. So the quantity x plus b over 2a squared equals this, means that x plus 2a is either plus or minus the square root of this thing. Okay, well, subtracting b over 2a from both sides, we get this. I'm not going to read it to you. This is very obvious rearrangement. And then expressing the square root of this fraction as the square root of the numerator over the square root of the denominator, we see that the square root of the denominator is perfect square of 2a. And now the denominator of this expression matches the denominator of this expression. And we can simply factor out the 1 over 2a, and we end up with this expression. And this is the standard quadratic formula. We followed valid mathematical operations from here to here, so every step here is equivalent to the previous, which means that if this is true, then this is true. And also, since every step is equivalent, we can go backwards along these steps, and from this we could build back to this. So if this is true, then this is true. So we have if this, then this, if this, then this, which means that this, if and only if this. And if you understand if-thens and if and only ifs, you get a good idea of what this theorem is telling you.